Hello and welcome. This is the first of a set of videos where I'm just going to work through all the practice problems in the new workbook, and I'll try to go through them in enough detail that you can follow everything. If I do something too fast or skip an important step, please get a hold of your instructor and we'll try to fill in whatever gaps there are. So let's get into it. This first section is about a formula that we usually write as either E equals mc delta t, that's the version I like, or Q equals mc delta t, I think that's the one in the lesson. And it's for how much energy it takes to heat up some amount of material. The E is your total amount of energy, as in heat, usually measured in joules when you're working in metric. M is the mass of the thing you're heating up. Could be a chunk of steel or a container of water or anything like that. Mass for chemists is usually measured in grams. We will see kilograms, but grams are kind of our favorite. We use capital T for temperature, and when you put a delta in front of something, it means the change in whatever that thing is. So if you used to be 6 and now you're 20, the delta of your age is 14 years. That's how much your age has changed. And it's the same with temperatures. If something was at, stealing from this example, 21 degrees and now it's cooled down to 13 degrees, the delta would be minus 8 degrees. So delta of something means the change in it, and that'll be measured in Celsius degrees generally. We don't do any Fahrenheit in this course. And C is either the specific heat or the specific heat capacity. It's a rating that every material has for how hard it is to heat up or cool down. Water and wood and concrete and plastic all have their own specific heats, and they're measured in kind of funny looking units. It's generally joules per gram degree Celsius. So this is saying for every gram of material that you heat up by 1 degree, it's going to cost you this many joules. And if there are more grams, it'll cost you more. If there are more degrees of temperature change, that'll cost you more, but they're all multiplied by whatever the specific heat number is. So let's try this out and see if we can defeat some practice problems. If you see the Q version, the only difference is the Q stands for quantity of heat, which is another way to just say how much energy is there. So they really do mean the same thing. In this case, assuming this is the formula we're going to use because it's the only one we know so far, they tell us the mass of a sample of water is 355 grams. We're talking about water, and its specific heat is a number you'll probably memorize soon enough. It's 4.19 joules per gram degree Celsius. That number's in the data book on page 3. If you Google the specific heat for water, you'll get 4.18 something. So this number is not the gold standard, but it's what we generally use in this course. And our temperature change, I already ruined the surprise on that, is from 21 to 13 is 8 degrees. Negative 8 degrees is technically better because the temperature went down, but for these calculations, the negative doesn't matter all that much, so you'll see I'm going to ignore it a lot. So if we do mass times specific heat times temperature change, and then we mash our calculators, 355 times 4.19 times 8, I get 11,899.6, and this is energy, so it's measured in joules. Now, significant digits. The mass we got has 3 sig digs. The specific heat of water has 3 sig digs, and looking at these temperatures, it is very tempting to say that our answer's got to have 3 sig digs because they do as well. The catch is when you subtract those temperatures, 21.0 minus 13.0, the answer comes out to 8.0. When you add or subtract, you take the same number of decimal places as these. And so we get 8.0, which means our temperature delta only has two significant digits, and that means our answer can only have two significant digits. So we have to hack this down, and either we go to scientific notation and say it's 1.2 times 10 to the 4 joules, or divide that by 1,000 and you can get 12 kilojoules. And there we are. So half the complication there was the significant digits. The formula itself, not too bad, I hope. Let's get a couple more reps in and see if we can get comfortable with this. Okay, 15.7 grams of copper is heated, and its temperature changes. So, same formula again. We need the mass of the copper, the specific heat of copper, and the temperature change for the copper. They tell us the mass of the copper is 15.7 grams. That's not too bad. The specific heat of copper is in the data book, and it's given as 0.385 joules per gram degree Celsius. Please resist the urge to Google stuff like this. If you Google specific heat of copper, you will get a number. It will be close to this, but it probably won't be exactly 0.385. And unfortunately, if you get a wrong answer on an exam or something because you went to some other source for your constants, there will be no mercy. So please stick with the data book. If you can't find something in the data book, check with the instructor. We'll help you out. What's the temperature change for this? We started at minus 20. We started with a freezing cold chunk of copper, and we heated it up to 25. The difference here is 45 degrees. If you do 25 minus negative 20, your delta is 45. And technically, because we're subtracting, 45.0 would be the right number. So, again, we times those together. 15.7 times 0.385 times 45. And I get 272. My calculator gave me a gazillion digits for this. It gave me 0.0025 joules. How much of that can we keep? Mass had 3 sig digs. Specific heat had 3 sig digs. Temperature change had 3 sig digs. So this one really is straightforward. We can give our answer as just 272 joules. Nothing too terrible. And then they do it again. A kilogram of mercury is heated from 22 to 200. How much heat? Same formula again, but they're messing with us in a couple minor ways on this one. First, the mass they give us is not in grams. But our specific heat is about grams, so this is no good. We can't have a formula where some of our stuff is in kilograms and some is in grams. A kilogram is worth 1,000 grams. Anytime you have kilograms, you times by 1,000 to get the amount in grams. So 1 times 1,000 gives us 1,000 grams of mercury. Now, mercury is not in our data book, so it's a good thing they bail us out in the question here. And you can expect this. We're pretty good on our exams. Either stuff will be in the data book or we will take care of it in the question. We're not going to ask you to memorize the specific heat of aluminum or anything goofy like that. So there's our mass. There's our specific heat for mercury. Temperature change. We're going from 22 up to 200. 200 take away 22 is 178 degrees. And so, again, we do a bunch of multiplying. 1,000 times 0.138 times 178. I get 24,564 joules. Trouble is, 3 sig digs, 3 sig digs. Technically, this 1.00 had 3 sig digs also, so I cheated a little bit by writing 1,000 here. Our answer can only have 3 sig digs, so we cannot write 24,564 with only 3 digits. Two choices. We can either go to scientific notation and write 2.46 times 10 to the 4 joules, Or we could divide this by 1,000 and get 24.564 kilojoules. Joules divided by 1,000 gives you kilojoules. And then if we take 3 digits of this, we get 24.6. And you're saying, wait, it says 24.5, what are you doing? When you cut a number off like this, if we're only allowed to keep 3 digits, that means we're keeping 24.5. But we take one last look at this 6 and say, hey, if you're 5 or more, we'll round up in memory of you. And because this is 5 or more, we increase our last digit by 1. In case you haven't rounded stuff in a while. Now you remember. So that's the MC delta T formula. I'm sure they'll have some nastier examples for us, so we will see those and you in the next video.